Personal finance presentation using OneNote. Present value and future value mathematical formulas, problem number 3. Let's talk finance, and this time it's personal finance. Here we are in OneNote. If you have access to OneNote, would like to follow along, you're not required to, but if would like to, we're in the icon on the left-hand side. We're in the Practice Problems tab down in the 1121 Present Value and Future Value Mathematical Formulas Prob 3 tab. Also note, when using OneNote, take a look at the Immersive Reader tool. Our presentations will also be in the text area. Same name, same number, but with transcripts. Transcripts that can be translated into multiple different languages and either listened to or read in them. Closing the icon, we got our information up top, calculations on down below. We're looking at the present value calculations, focusing in on mathematical formulas this time. But before we get there, let's review some of the other ways we've gotten these calculations done in prior presentations. You do not need to have done those prior presentations to move forward here, but we want to see what the different formats can be so that we can pick the best method for us at a particular point in time, and so that we can see how other people might do the same thing in a different way and be able to follow along. So the information up top, we have the yearly earnings percent in a savings account, meaning we're expecting or theorizing that the amount will be going up by 18% each year on an annual basis. That is, of course, high for a savings account at this point in time, but you can think of the same concept for anything that you would expect to be going up in value, including like a home, land, stocks, bonds, some type of investment that we're expecting to be going up, 18 being a higher percent than some of the prior practice problems that we have been working with that we want to look into. So how long will it take for the account to double? That's going to be the first question that we asked. We can ask that question without even having an initial investment amount by using, say, the rule of 72, which we then down here taking in essence just simply 72 divided by the rate, but in number format, 18 instead of 18%, gives us approximately 4 years. Now, then it's useful to apply out or think of an actual investment amount, which here we're going to say $3,000. If they don't give you an investment amount, and it's like a book problem or test question, and you want to make it more concrete in your mind, then you might pick something like 100 or 1,000 or 10,000 or something like that. We're going to be using 3,000 here just to, again, differentiate it from prior practice problems. Therefore, the doubling of it would happen when that 3,000 gets to 6,000, which, given the rule of 72, would be about approximately 4 years. Now, we then did a running balance calculation, which, no matter what method we use, is useful because it actually gives you a pictorial idea, much better conceptual framework in your mind of the increase of the interest from period to period, looking at that compounding. And then, of course, that happens once again between 4 and 5. So it's a little bit over 4 years because 4 was an approximation to get to then the doubling from 3,000 to 6,000 as we see in our running balance. We then did our calculations with the Excel functions, and we used 3 different functions to get to the answer, including the present value, the future value, the net present value. We're going to do a similar concept here, noting that when I use a present value, whether I'm looking at the formulas as we will do this time or the functions as we see in Excel, the end result of that calculation will be the present value, meaning if we take the data that we currently have here, we would assume that we know the end result, which is the future value of 6,000 in this case because it's double the 3,000. And the present value then would be the 3,000. We're really looking for the distance between, and we know the rate, which would be 18%. We're really looking at the distance then, the time frame between those two components. The result of the present value would then be the 3,000 that we would look for. Now, again, the thing we're looking for is the unknown, which is the number of periods in this case. And when we used our functions, we had to either use another function to get that unknown, or we had to use basically goal seek to figure that out, whereas we couldn't just adjust the formula as we can do if it's a mathematical formula, which we can rework algebraically. We also looked at it in the future value, and again, with the mathematical formula or with the Excel function, future value means that the end result would be where we stand in the future. So we would put into the formula the present value, the 3,000 plus the rate that we expect on the return and look to see what's going to happen at the end point, which would be 6,000, which again, in this problem, we already know. The thing we don't know is the number of periods, which we kind of backed into using goal-seek. And then we used another formula to basically actually solve for that one point, the number of periods directly, which is similar to what you do if you were reworking your algebraic equation to solve for the unknown component. Okay, so then we're going to go down here to the current format, which is going to be the mathematical formulas. We'll do in essence the same thing we did with the Excel functions mathematically here. We'll do it from the present value side, the future value side. We won't have a formula for the number of periods because what we would typically do in practice, although if you look this up in a book, you might see a formula for the number of periods. In practice, you'd probably say, I'm going to use either present or future value formulas, plug in all the unknowns, and then solve algebraically for the unknown, which in this case is n. If you were to rework the formula algebraically solving for n, then you would in essence do the same thing as we did here up here with the function, reworking the algebra and solving it for basically the one unknown. All the formulas, however, you can see are basically going to be related. So typically we'll use something like the present value. We'd say, okay, let's look at the present value formula. Present value equals the future value, which you could say times or over 1 plus the rate to the number of periods, which would be n. And then we can plug in what we know. In this case, we know the present value, the starting point, which is 3,000, equals the future value, which we know is twice the 3,000 because we want it to double, which would be 3,000 times 2 or 6,000 over or times or over 1 plus the rate, which is 0.18 or 18% to the caret of n being the unknown. So you can write it out algebraically looking something like this. 3,000 equals 6,000 over 1 plus 0.18 to the power of n, and then solve for n algebraically. We will not be solving for n here. I'll let you do that yourself and work through the algebra if you want to work on it in that format. That's the way you would do it if you had a test question. If you then, another way you can look at it, and this will give us a clearer understanding of what we did on the Excel functions, and it'll help us practice putting data into a table, which is not something you often learn in courses at schools, but it's something that's quite practical in practice. And then we can see how you can use the goal-seek feature and how that works both in terms of a formula, a table, as well as Excel functions. So if you were to put this calculation into an Excel function, kind of like you would see in a format in a financial statement or in a tax return or something like that, we're just going to want the numerator and the denominator in the outer column. So what I'm going to do is start off with the future value, which I didn't label here for some reason, but it's going to be in the outer column here, and that's going to be the 3,000 times 2 or 6,000. And then we're going to take the denominator, which I'm going to put as a subcategory underneath, and pull that into the inner column. Since there's more detail in the calculations, I'm going to indicate with a colon that we will pull this to the inner column and that it is a subcalculation of our end calculation. We're then going to take the 1 plus r, so 1 plus the rate, 18%, which you could type in here with a 0.18 or 18%, noting that the 1, obviously, it needs to be lined up with the same formatting. You can put it as 1 or 0.1 or 100%. And that would then give us, if we added those up, we're going to give a subtotal here. So we got the 1 plus the 0.18, 118, 1.18 or 118%. And then we have the number of periods. The number of periods is the unknown. Notice that I'm not reworking the table to solve for that unknown, meaning I'm not trying to rework the table to get the end result to be the number of periods, but rather I'm going to show that that cell is the unknown, and I'm going to make it yellow, and then I would use the same kind of goal-seek function or feature over here to say, I'm just going to plug something in here. Right now it has the current answer in it, but if I don't know the answer, I could put like 10 in it, put something that doesn't leave it as blank, because if it was 0 or blank, it could mess up the actual calculations, whereas you want some number in there, so we'll calculate something. Then we take the 118% to the power of 4.19 about, and that will give us our 2, in this case, that being the answer. And then we got the numerator and the denominator in the outer column, 6,000 divided by 2, giving us then the 3,000. Now, if you set this up in a table such as this, and you had some number other than the answer here in the number of periods, something like 10 or something like that, then you can use the same concept that we did with the formulas and say, okay, instead of me reworking the algebra, I want to ask Excel to change this number to what it needs to be in order to get the end result to what we know it needs to be. We know the present value needs to be the 3,000, future value 6,000, present value then the 3,000. And then Excel will use trial and error, in essence, to just basically populate that number. Very useful tool for longer spreadsheets, for a spreadsheet kind of format of a calculation, and to understand how to use that algebraic concept with a basically brute force kind of method of trial and error type of method. Also very useful for functions. Let's do the same thing down here with the future value. So we could have done, and this is another way, if you work these formulas, you might, one person might say, hey, I'm just going to plug this into the present value formula. And another person might say, well, I'm going to use the future value. That's just what clicks in their head, or that's the first thing that pops into their mind. They could do that, and they'll get the same kind of thing. In that case, we have the future value, which would be the twice of the 6,000, the ending point, that as the end result would be equal to the present value, which is the starting point in our formula, which would be the 3,000, times the 1 plus the rate, which would be the 0.18 to the power of n. Looking something like this down here, 6,000 equals 3,000 times 1 plus 0.18 to the power of n. Then, of course, we can solve for n once again. Or we can populate this, as we'll do down here in the table. We're not going to rework this one to solve for n in this format, but solve for the future value. End result then is known to be 6,000, the unknown being the n, which we're going to back into and imagine a trial and error format for doing that. So if we build up this table, I want these two major components in the outer column, any more complex detailed calculations in the inner column. So the 3,000 I put in the outer column here for the present value, and then we're going to say this more complex 1 plus rate to the n is a subtotal calculation that we're going to pull into the inside, indicating that with a colon and the indentations. Then we're going to take the 1. Notice I represented it as 100% this time. 1 is 100% if we put it in a percent format. And then the rate, which is now represented as a percent, or 0.18 as a decimal. Adding those up, we're going to get the 118. We take that to the power of the number of periods, that being the unknown. So if we didn't know this, this happens to be the answer, of course, again, then we can plug something in there, trying to put something other than 0 or a blanked cell, because those two amounts could populate or mess up the calculation, right? It could give you an error message depending on what the math is that you're entering. So you want to put something like 10 in there, and then we're going to go back and make it yellow to indicate that I'm going to go back and adjust that when necessary, and we're going to take that then 118 to the power of 4.19. We then get 2, and now we've got these two components, so we can multiply together the 3,000 times 2, which is going to give us the 6,000. Once we have this all connected, we could do it algebraically with a calculator, and we can manually adjust this if we put something like 10 until you imagine you get to that end result to be what it needs to be, 6,000. Very tedious to do with a calculator, very tedious to do in a test situation, but quite easy to do with Excel in practice type of situation with something called the goal seek. Now note, if you're in a test situation and you need to calculate this component right here to the power of 4.19, make sure you got a calculator that handles that calculation. So we're going to go to the standard calculator. We want to go to a scientific calculator in this case. That'll do it. We're going to take the 1.18 and take that to the power of x to the y, gives us the little caret up top, and that's going to go 4.19 and enter, and that's going to give us about 2 because this is a rounded number, and then we got our 2 here, and you can carry on from there. So I'm going to make this a little calculator again. So there we have it. So there's our future value. So notice this gives us a similar kind of result as we got when we did our Excel functions, which is great, but it's still kind of a magical answer in that it doesn't really tell us how the compounding works, which is why you might still want to do a running balance table. Also note that if you do calculations that have a lot of present values within them, like capital budgeting decisions and whatnot, this can be, of course, quite tedious And if you're in a school like in practice, of course, you would then use Excel, and it's no problem at all. You just got to figure out how to format your tables best. But if you're in a test situation or a school, they might try to take away your calculator, and then they're going to give you the tables. So then we're going to do next time the same kind of calculations using tables, or at least consider how we could do that and some limitations with the tables, which you could find, note this 18% quite high for tables, and that might be a limitation that we'll run into and discuss that as we go there, and then how schools might adapt their questions if you're working in a school setting. And so you can kind of be aware or predict what they're going to do based on the limitations if they're going to use tables.